Okay, I'm Harrison West, and this is my project predicting the release years of album covers with inductive transfer learning. So, I want to talk about convolutional neural networks. So, they're the basis for the majority of computer vision tasks, um, and they enable great generalization due to the convolution kernels that can slide over the image um, and make these 2D feature mappings and then zoom in, right, capture all the features of the image. A big problem for them, however, is the scarcity of labeled training data because it's hard to get or because, it's hard for humans to go through and label it all, especially if you assume that the training data and the test data have to have the same distribution. And so what would be great is if we could use some other data to actually learn what we need to learn. And that's where transfer learning comes in. So it's the application of knowledge from one domain to a related domain, from the source domain to the target domain. It applies to human learning too, right? Knowing violin is probably going to help you learn piano. But the domains do have to be related, right? Knowing how to ride a bicycle is probably not going to help you to learn how to play piano. So there's lots of types of transfer learning. We can talk about, which data is labeled. So if there's no label data, it's unsupervised, and that makes sense. If the label data is only in the source domain, it's transductive. If the label data is in the target domain, it's inductive, and then we can further divide that based on whether it's available in the source domain. If it is, it's multitask. If it's not, it's self-taught transfer learning. So four types there. And then we can also think about the feature space. So it's homogeneous if the domains are of nearly identical feature spaces or identical. And it's heterogeneous if the domains are of different feature spaces. And we'll talk a little bit about what that means. Um, so the problem that we're tackling here is with a target domain of album covers, we want to predict what year an cover came out. So we want to look at this background and say 2015. Um, and the background that I have right now, 21 Pilots album, Blurry Face, great album. Um, the source domain is object classification models. So we looked at some of those in class, right? That can identify a water bottle or a toaster. Um, and you'd think, what does that have to do with predicting the year of an album cover? Well, it really helps to know just what an object is, right? So you're not just flying blind, looking at pixels, looking at numbers, right? If you know what an object is and how to like delineate objects from other objects, what an object boundary looks like, that already is a huge head start. And we'll see how effective that makes our model. So this is an inductive multitask homogeneous model. Inductive and multitask because label data is available in the source and target domains, and homogeneous because the domains have the same feature space. They're different distributions. That's what makes it transfer learning, right? But it's the same feature space because we're looking at image data. If we were trying to use audio to learn something about the image data, that'd be heterogeneous transfer learning. So originally, I approached this problem as a regression problem where given an album cover, you'd predict its release year. Um, and I used the range 1950 to 2022. The problem was I used this loss function that penalized predictions far from the true release year, right? Because if we guess 1952 and it's actually 53, that's really good, right? The disadvantage is that the model would start centering, right? When I ran these models, they did okay in terms of accuracy, right? You'd expect in that range, you'd expect a random chance to be off by about 25 years. Our model was off by about 18 years. So that's fine, you know, but the disadvantage was the centering. It would never predict that an album was released in the 50s or the 60s or the 2020s, right? It would always shoot for the middle. Um, and so you didn't feel like you were ever getting an accurate representation. It was just trying to minimize that loss by guessing close to the middle. So that's when I turned it into a classification problem, where given an album cover, you predict its release decade from the 1950s to the 2010s, so 7 decades. The disadvantage is we are losing some data, right? We actually know the year an album was released. And so we can, we don't have the nuance of the difference between 1950 and 1959. Um, but the advantages are that we can use now a categorical cross entropy loss function. And so we won't have any centering. Um, so we're okay actually saying, okay, if it's actually from the 50s and we predict the 60s, we're okay with penalizing that the same as we penalize a guess of the 2010s. Um, and that way we can actually draw conclusions from trends in the confusion matrix, right? If the two decades are often confused for each other, we know that it's probably due to some real pattern in the data and not just, you know, the model trying to fit the loss function. So the data collection, we use the Spotify random library of Spotify, which is the way to interact with the Spotify API in Python. Um, so you can get like a random album from a given year. We filtered out some albums with non-English characters, um, and some explicit albums, just because we wanted to make the data more homogeneous. Um, we saw, I looked at some Chinese and Japanese albums, right, that really um, just were so different from all the other albums in the list, even if they were released in the same decade as those albums. And then we just don't want to be scrolling through a bunch of explicit albums. Um, and so in total, there's 836 albums from each decade exactly. And there's a nearly even split from each year within the decade, about 83. And then that's split evenly 80-20 into train and test data. Um, so moving on to the model architecture, we start with our base model, our object classification model, and we used um, we used three different options for that. Um, then we had a flatten or global average pooling layer depending on the base model, depending on which one worked better with the base model, and that kind of allows it to extract those 2D features. Then we have a dropout layer with 30% dropout, then a dense layer with 1,024 neurons and rectified linear unit activation, followed by a predictions layer with softmax activation. Our optimizer was STG with learning rate of 0.0001, momentum 0.9. And we kept all those the same for the three different base models that we'll look at in a second, because we want them all to be in the level playing field. So results. So here's a comparison of the three base models we used: Inception v3, VGG19, and ResNet 152 v2. I'm not really going to go into detail on these, stats. You can take a look at them. I couldn't find any discernible trends in how those stats were affecting the results, but here are the results. So there's the decade accuracy. Inception v3 at a 31.2% decade accuracy, so it predicted the right decade 31.2% of the time. VGG19 did that 34.5% of the time, and ResNet 152 v2 did that 35.5% of the time. Random chance we'd expect a 14.3% decade accuracy, so I'm pretty happy with that. Well over double what random chance would predict. So we can look at some of the model accuracy trends. You can see Inception v3 actually doesn't clear 0.5 even for the training data, and gets up to about 0.3 for the validation data, whereas VGG19 is going to almost clear 0.6 on the training data, and ResNet 152 v2, the best model of the three, cleared 0.35 on the validation accuracy and about 0.55 on the training. So here are the confusion matrices, and this is really the meat of the data because we can look at, what decades are being confused. So one obvious trend, and I'll just scroll through these, they're actually all very similar. There's VGG19. So you can see, more accurate. We're getting some more alignment down that center diagonal, and ResNet 152 v2, the best model. So you can see they're all kind of similar. Really good on the 50s and 60s. And you can see that, decades that are close are getting confused for each other more often. So 60s and 50s are getting confused pretty often. And you can just look at that diagonal from the top left to the bottom right, and you can see that generally the weights are higher close to that diagonal. Not always true, but you can see that too. Some discussion, and I'll go back and kind of explain these. I'll go back to those confusion matrices. But overall, our models were successful with up to 35.5% accuracy. So that's a success for the inductive transfer learning model that we used. The predictions trend toward the correct decade. We just talked about that, right? So we see a lot more activity around that center diagonal. And then new albums are confused for old albums more than vice versa. And so I'm going to nickname this the nostalgia zone is greater than the ahead of its time zone. So the nostalgia zone is that bottom left corner. And the ahead of its time zone, right, is the top right corner. So the ahead of its time zone is albums from the 50s and 60s that, according to the model, look like they're from the 2000s and 2010s. The nostalgia zone are albums from the 2000s, 2010s that are made to look like, or at least the model thinks they look like the 50s and 60s albums. And those definitely like are sometimes made intentionally, whereas from the 50s and 60s, right, it's hard to predict the future and know what albums are going to look like. So to me, it makes sense that this bottom left um, part is more concentrated. You can especially see it in the Inception one. So you can see there a bunch of single digit numbers in the top right, and then no single digit numbers in the bottom left. Um, and then we could also see some groupings. So, I mean, you notice in all of these, it really struggles with the 90s. In VGG 19, it barely does better. Like, if it's given a 90s album, it has no idea when that album came out. Um, you can also see these squares, right, that are starting to form um, around the 50s and 60s. Seem like they're going together, which to me, that makes sense. When you reach 70s, you don't really think old timey, but even in 60s, I feel like I can picture some old timey albums, some black and white, some really candid photos of the artists. So I think that makes sense that there's a strong correlation between the 50s and 60s there. The 2000s and 2010s is interesting, and I'll get to that later, why maybe that could be a really logical grouping. And then the 70s and 80s, you can also kind of see. So here you see that those squares really strongly, right? The 70s and 80s, you start to see a square there. There's some confusion there. And then the 90s, maybe they were just too artsy, right? And um, we see artsy albums from every era, and maybe the 90s was just too artsy and um, you know, couldn't uh, have good predictions. So there you go, groupings, right? We saw some logical groupings um, in the confusion matrices. So a conclusion. So transfer learning is the application of knowledge from a source domain to a target domain. It's great for computer vision tasks, and we can divide it into different categories. So we looked at an inductive, multitask, homogeneous transfer learning task, um, and we tried out some different base models, some image classification models that actually helped us to predict the years of album covers. Um, and with ResNet 152v2, we were able to predict the correct decade with 35.5% accuracy, even though with random chance, you would only get just over 14% accuracy. We looked at some trends in the data um, and how there's some logical groupings between different decades, how 50s and 60s are a lot closer than 50s and 2010s, for example, and that nostalgia zone seems to be bigger than that ahead of its time zone, right? Um, as for future work, one thing I'm interested in is did changes in the calendar affect album covers? So does the start of a new year, decade, or century actually make a difference? Is there actually a bigger difference between the 1999 year and the 2000 year than the 1999, the 1998 year? Like maybe as a decade comes around, as the arbitrary restraints of the human calendar maybe that actually makes a difference in how people think about what album cover they should release in that year. Um, you'd probably need a lot more data to capture a trend like that. I think it's quite possible. Same thing even with maybe odd and even years. Something about, how you look at an image and you associate it with, oh, that's a one type image or that's a two type image. At least I do that. I've heard some other people do that. Maybe there's a difference between odd and even years that we can actually, maybe 2006 is closer to 2008 than it is to 2007. These are things we need more data to really hammer that down. I certainly think those are possible. Um, and then we can also look at do modern albums imitate some past decades more than others? And we can look at that a little bit, right? In the confusion matrices. Okay, so we're nostalgic for the 80s, apparently, in the 2010s, according to ResNet. And then VGG 19 thinks we're more nostalgic for the 70s. We need, again, more data to really hammer that down. Um, and with that, here are my references. Thank you all so much for watching.